Good afternoon, everyone, and a very warm welcome to all of you. Thank you for joining us today for this insightful masterclass on model assessment and selection for machine learning, hosted by the London School of Hygiene and Tropical Medicine. My name is Shweta Gautam, and I'm the Client Engagement Manager at StudyIn, and I will be moderating today's session. At StudyIn, we work closely with leading global universities to support students in exploring international education opportunities. This exclusive masterclass will focus on model assessment, validation techniques, and performance optimization, and will provide valuable insights into applying machine learning in global research and public health contexts. We are delighted to be joined today by distinguished academics from LSHTM, Dr. Stephen Hu, Associate Professor of Epidemiology and Bioinformatics and Program Director of the MSc Health Data Science at LSHTM, and Dr. Per Maslow, Assistant Professor in Statistics and Environmental Epidemiology, who will be leading today's masterclass. We are delighted to have you with us today. Before we begin, a quick note for the participants. Please feel free to share your questions in the Q&A box available at the bottom of your screen. We will address them towards the end of the session. So without further delay, I would now like to hand over to Dr. Hu and Dr. Maslow to begin the masterclass. Over to you. Thank you.
Thank you very much, Sudha. I just wanted to say thank you very much for having us. I think Pierre is going to take the microphone now.
Yes. So thank you very much all for attending. Yeah, there are many of you, so I hope I can give a proper masterclass today. So the topic we chose was on model assessment and selection in machine learning, which is, in my humble opinion, a key element of any machine learning analysis and model building. And so the idea of this quite short lecture today is really, well, first to understand a little bit of the underpinnings, the theoretical underpinnings of what we call model complexity and the bias variance trade-off, to really make this distinction between training error and test error, and I will define that a bit later. How cross-validation work to assess model performance, and so with all of that, to be able to choose adequate machine learning models. So, but first, before going really into the core of this topic, just a very quick recap of what we call here supervised machine learning. And the idea here, our objective when we do this task, is that we have a target, so what that I call Y here, that we seek to understand and especially make predictions on. So, for instance, this target Y can be blood pressure or any measurements, and you have new patients or new population, and you want to predict what this target will be in a new patient, in new observation. And so to make this prediction, we assume that our target is associated with some predictors, so potentially many predictors that I call X1, X2, etc., XP. And so we assume that this target is associated through an unknown function that I call F. And in addition, this target also includes some error, some irreducible error. There is a part of this target that we cannot predict with our predictors. And really, under the hood, our objective is to learn this function, try to learn it as closely as possible, to be able to make good predictions of our target. So examples of model to learn this function, probably maybe you've heard of some of them, but the simplest one might just be linear regression. So you have some predictors and and your target, and then you make prediction as a linear combination of your predictors. So if you have just one predictor, for instance, this will just be a straight line. So your prediction will be a straight line like that. On the other end of the spectrum, we have something like the k-nearest neighbors, for instance, where the idea is that when you want to make a prediction somewhere, you look at your observations that are the closest into the predictor space, and then your prediction will be like the average of all those observations. And there are many other models. Another example is the neural network. So this is neural networks are really the model that are at the core of what we now call deep learning. But here it doesn't matter much which model you use. It can be any model as long as you have one model that makes prediction of your target using the predictors. A good note also on prediction versus inference. So, maybe if you followed some statistics course before, this course might have focused more on inference, where in inference, the idea really is to focus more on the interpretation of this association between your target and the predictors. And so in inference, usually you will use linear models or relatively simple models that can be interpreted with a focus on the parameters. Here in machine learning, we are much more focused on predictions, which means that our sole objective is really to provide good predictions of our target, and the interpretation is really secondary. There might be some interpretation elements, but it comes really after. And in machine learning, we are of course much more comfortable with this so-called black box model, where we don't really understand or we don't really know all the details of the parameters as long as our predictions are good. And the objective when you do this kind of machine learning analysis, when you want to build a machine learning model, one of the core elements of this objective is really tuning and model selection. So most models, the only exception really is the simple linear regression. But otherwise, all of the models will have what we call tuning parameters. So these are parameters that you need really to fine tune, as the name indicates, so that your model performs well. So that can be the number of variables. For instance, if you consider a very large linear model, that can be the number of neighbors in the k-nearest neighbors. That can be regularization parameters in neural network, but also in other models like Lasso or Ridge. This can be any kind of different parameters, but you will always need to choose these parameters. And in addition to tuning, you have model selection. Say you are not sure whether to use nearest neighbors or neural networks or Ridge or anything. Which model should you use in practice? And so you have a very similar objective here of really choosing which model you need to apply. And so what we are looking for now is a way to compare model, some criterion that will tell us, okay, you should consider this tuning parameter, you should consider this model for your prediction. And so a very, very simple example is here, say that we have this data set here with the gray dots, and we have three models. So this red line, which looks way too simple to make our predictions. The green model, which actually seemed to capture the general trend, let's say, and the blue one, which is really wiggly. And so we are thinking maybe this one is too complex or there is a kind of overfitting. And and the idea is now which is the better model. And of course, this is a very simple example. In practice, you will have potentially many more models with many dimensions, in the sense that it will be very difficult to look at them simply on a scatter plot. But this is the core idea. And so we need a way to assess a model, to measure the quality in our model, to make this prediction. And so the idea really is to have a criterion that tells us how good our predictions are from our model. So this model should be able to make good predictions of our observation. And so this measure, this way of measuring our model quality that we say, is really a measure of the error we make in our prediction. And so a simple measure that we can work with initially is this mean squared error, and the development, well, what I show later is really based on this mean squared error. But how we measure this error that we make in our prediction is that we take the difference between our observed target and the prediction we make, and we put that to the square, and we take the average of this squared difference. And so, like visually, this looks like this. You have your line, for instance, if it's a linear model, you have your observation, so the prediction would be along this line. And this squared error here is like it's the area of this square here in our error. And so here we have a straight line that goes straight through the points, and that seems to be a good fit. We have small squares with small areas. Here we have a line that is much less good. And so in this case, we have big squares. And so the sum of the area of all the squares will be high. And so this is the meaning of this mean squared error. And this is really the most classical measure of error in a statistical model. And so initially we can think, okay, we can use this MSE to select our model. We can compute this MSE for our different models and then select the one that has the lowest value MSE. And in that case, you can see that we have computed these values here for the free model. And the lowest value is for the blue model. So this is the blue that on average has the smallest square distance to the observation. And so in this instance, we would select the blue model as the best one. But there is a catch, though, is have we really selected the best model? And just using this MSE like that, so we fit our model and we make our prediction and we compute the MSE, actually, we can show that we will always select the most complex model among all the models. Because, well, this most complex model will fit the observed target very closely. Because it can like it's much more flexible, and so it can really very go closely to our observations. And so I will show that it's not the best strategy because. Recall from earlier that when I defined our machine learning objective, our target is includes two components. The components that can be predicted by our predictors, this association here, but also this error component, so additional variation, what I called irreducible error before. And what happens when we have a model that is too complex is that actually it will start to try to also model this error that is not part of what in Y is actually due to its association with X. And so it will try to reduce this error way too much. This is what we call overfitting also. Yeah. And so the idea is really to see that we are not really, in practice, we are not that interested in what we call training error. So in taking our observation, fitting a model, and then measuring the error on the fit, because as I just told, it always favors the most complex model that will reduces residual, this error, too much. In general, we are much more interested in a model that generalizes well, which means that it will minimize this mean squared error here, but on what we call a test sample or a validation sample, depending on the context. But the idea is that we want to measure this MSE on new observations that have not been used to train a model. And this makes sense because if you remember, I gave some example at the beginning of the lecture saying, oh, say you have your machine learning model and you have new patients, for instance, and you want to predict what will be their blood pressure or any outcome of a disease or of a treatment, for instance. And so what you want to do is that you want to make good predictions on new patients, on new observations. And so what you want to measure at the end of the day is a model that makes good predictions, not on the data that you use to fit it, but really on new data that will come later in the model's life, I'd say. And so this MSE, we call this the test or generalization MSE. And so I wanted to show a bit what happens and why we can't use the training MSE. This is the MSE that we compute directly on our data that we used to train our model. Is that this training MSE, we say that it is optimistic. So I will spare you the mathematical details. But what happens is that this training MSE that I just called MSE later, we can show that it's equal to the true, well, here it's a typo, it was test MSE, but minus some term here. And this term is the covariance between our prediction that we make from our model and our target. And so this term here can actually be seen as the complexity of the model because since it's the covariance between our prediction and the true target, basically the most complex our model, the closest our predictions will be from our target, the training target, and so this term will be very high. So it means that these terms will become higher and higher the more complex our model is. And so it means that the difference between our generalization MSE, our true target, our true objective, and the training MSE will become bigger and bigger as when the model increases. And so you can see that in practice, you will have something very similar to the plot on the right, in the sense that you have your generalization MSE in red here, and when you increase your model complexity, it will improve up until a certain point, where at some point the model will become too complex, and then our MSE will then become worse and worse. But the difference with the training MSE will increase, and the training MSE will continue to decrease always. So this is why we cannot really use the training MSE to select our model here. So a quick note. So this development has led to some criteria that we can use to estimate our generalization, our test MSE. Typically what we call the Mallows CP and the AIC. So this term here, this complexity term between the covariance and target, sometimes you can also see it referred as to degree of freedom, because for instance, if your prediction model is a linear model, this will be equal to the number of parameters in your model. So it fits closely to the degrees of freedom. But this suggests a strategy to evaluate to correct our training MSE to estimate our generalization MSE. And so, for instance, you can compute the malloc CP, where there have been a mathematical derivation of this term that you can then write this way. So you recognize here the 2 out of n, for instance, that we have here, and this covariance in some model reduced to here the number of parameters times this is the residual standard deviation here. And you have also the AIC, the archaic information criterion, that is a more general version of this malloc CP. However, these criteria are very useful in some specific instances, typically, mostly when your model is linear. So it's fine for some linear model, also some nonlinear models like splines or anything that can be cast as linear model. But for many other models, they won't give you a good estimation of this generalization error. So things like neural networks, random forest, for instance, and so on. You won't have very good approximation of this malloc CP and AIC. And so it's in most instances, and even for linear models, you actually have a much simpler way to estimate this generalization error. And maybe you already know that and you saw me coming from far away, but it's usually easier to simply compute the test error by actually, so when you start your analysis, you want to train a model, you remove a chunk of data from your data set, so say 20%, for instance, before doing any modeling, and this will be the test data set. Then you just keep the rest, the 80% you're left with, and you train your model on that. And once you've trained your model, you can predict on the test data set, so this initial 20%. And so on those predictions, since it's part of your data initially, you can compare your predictions on this test to their actual value of the target Y. And so with these predictions and the actual value, you can compute the MSE by comparing these predictions and the actual test outcome. And so it gives you a nice estimate of this generalization error. And so if you do this with our free model here, we can see that actually and now it's the green model that has the highest MSE test, so the MSE on the test error. And you can also see that always this test error here is higher than the train error, because this train error is too optimistic, as I showed earlier. So another element of choosing the best model. So yeah, what happens here is that we have found that actually the best model is the green one here, which is not necessarily the model that fits the most closely to our data. So what happens exactly is that this test can be separated into what we call the bias variance decomposition. So our MSE on the test, we can show that it's composed of 3 components. So an irreducible error. So the MSE test can never be below a given value, because this is the part of your target that cannot be explained by X. So this, we cannot do anything about it. There is a bias. So the bias is a systematic error, let's say, on average, what is the average difference, the difference between your average prediction and the average of your target, and a variance, which is more of the volatility of the prediction. So how much your prediction vary a lot? Is it very wiggly or not? So yeah, to give some example, typically bias shows how accurate the model is. And so it measures if predictions tend to be close to the true values of our target, while variance is more of a measure of stability. So here, for instance, you have a biased but low variance model, which is a typical linear model. You can see that if, for instance, I do this model on new realization of the data set and so on, you will always have very similar fits, very similar predictions all the times. So it means that it has low variance. But since the model is very, very simple, it means that your predictions will tend to be on average quite far from the target. On the other hand, you have a low bias and high variance model here. So it's very wiggly. So the model will tend to try to fit quite closely to your observation. But at the same time, it's high variance in the same that it varies a lot. If your data set changes only a little bit, it can have a massive impact on the predictions that you make. So it has high variance. And so there is the best model find a trade-off between bias and variance. So very simple models will have important bias but low variance, and very complex models will have low bias and very high variance. And so the idea is that we want this model that that find the best in between the two. And so usually you will find that your test MSE will have this kind of shape where with model complexity, it improves until a certain point where after that, it then re-increase and so on. And then your model is getting worse at predicting. And so what it happens with bias and variance is that the initial improvement is due to a decrease in bias because you gain in complexity. But at some point, your bias doesn't improve much. But on the other hand, your variance increases. So at some point, you don't improve your bias much, but the variance continue increasing with the complexity of the model, which means that your predictions tend to become worse and worse. And for someone who has a, let's say, typical statistics training, let's say, where you, for instance, when you read about the theory of linear models, you talk about the best linear and biased estimators or this kind of stuff. It means that usually the best predictive model will tend to be a little bit biased, which can be a bit uncomfortable for, let's say, a typical statistic theory, let's say. But having a bit of bias usually allows really to improve your prediction. So there are some limits to the test error that I showed. So the test error, it relies on really splitting the data set, and the key assumptions for this test error to work well is that the distribution of the training and test set are identical, but also that they are independent. And so there are situations in which this strategy is not optimal. Because in strategies in where you don't have that many data, so you have a relatively low sample, it means that all the observation in your test set will not be used to train your model and then to have a good estimation of this generalization error. And in the case of rare outcome also, it might be that when you do the splitting, you by chance, you select too many of these outcomes in your test set and not enough in your training, or on the other hand, too many in your training and not enough in your test, which means that it will be difficult to have a good idea of your training, of your generalization error. And so this can be generalized by cross-validation, which makes a a better use of your data set to estimate this generalization error. So what is cross-validation? It's a resampling method because the idea is that it involves refitting the model multiple times on different subsample of your data set. So really, it replicates the splitting into train and test that we just did, but several times. And so the core idea of cross-validation is really to split our data set into several what we call folds. So for instance, 5, and I will show some example later. And each fold will be iteratively become the test set. And so we will fit our model k times and then test on k different sets. And so it allows a more efficient use of the data because all of your data sets at some point will become, all of your data points at some point will be a test data point, and at some point there will be some trained data. So it means that even if you were to select too many of rare outcomes or not enough, over the different folds it will average out. But it is also more computationally expensive because it means that you have to fit your model several times to have to get this generalization error. So to illustrate how it works exactly, say we have 100 observation. We split, we permute this observation, or we shuffle this observation, and we split our sample into 5 folds, for instance. So here K would be 5. So each fold includes 20 data points. And so after that, you do your cross-validation. So if you have a 5-fold, you have 5 rounds. So in the first round, you set aside the first fold, you train your model on fold 2 to 4, and then you test and you compute your MSE test on fold 1. So you predict on fold 1 and then compare to its observed target. Second round, you do the same. This time you set aside fold 2, you train your model on fold 1, 3, 4, 5, you test on fold 2, and compute the MSE and so on, and you do this 5 times with each fold. You end up with 5 values of MSE test, and your final estimation, your final criterion is the average of these 5 values of MSE test, and then you select the model that minimizes this MSE test. So usually once you've selected this model, then you retrain this selected model on the whole data set, because here really the idea is to select the best model. A special case of this k-fold cross-validation is the leave one out cross-validation. Here, k is n, so the number of data points. So in our example just before, each fold you will have k equal 100, and each fold include just one data point. So it means that you do this 100 times. And so it's the same in round 1. You just set aside the observation 1. You train your model on observation 2 and 2n. You compute the square difference on the observation 1, and then you average everything out to get the mean squared error. And so you repeat and you repeat. So the question now is, what is the optimal number of folds? So for instance, should we do leave one out cross-validation, or should we do a k-fold cross-validation with a small number of folds? And so for instance, when you do leave one out cross-validation, your training set will be quite large. So you have what we call a lower bias in estimating your MSE test. It means that when you compute your MSE on the predicted observation, you end up having a better view, like a better picture of what will be the actual prediction error once you deploy your final model, let's say. However, there are more risks of correlation between the tests and train each time, which can make your MSE a bit too optimistic. But the biggest issue with leave one out cross-validation is that it's really demanding computationally. So if you have a very big data set, that would mean, for instance, you have 1 million observations. That would mean fitting 1 million model, which in most cases, it's really not feasible. So the k-fold cross-validation, you have a smaller training set. So it can be an issue for small data sets, for instance, because then your training model each time could not be as good as it can, will never be as good as then when you have trained your model on the full data set before deployment, say, but it's also more efficient computationally. But like a good rule of thumb, to be honest, that I go with is that in most instances, taking k equal 5 or k equal 10 will be a good compromise. So k equal 10 means that each time we will train your model on 90% of your data, which in some cases you will have like it allows for good picture of your actual MSc. Generalization MSc. Yeah, so there are some, of course, pitfalls for cross-validation, and one of that is that your data, when you create your folds, you should split your data in a way that your folds are all independent. Because basically, if they are not independent, you have some information from the test set that leaks into your training. And so it means that you end up with some measure of error that are too optimistic. This is something that can be an issue when your data are structured spatially or temporally. For instance, if you do geostatistics or you have time series, this can be broken. There are techniques, however, that can be used to alleviate this issue for spatial or time series, one of which can be to split your data by block instead of fully randomly. So for instance, if you have several years of data, you can split your fold into 1 year of data. And so you will less have this issue of dependence between training and test. There is some issue of data leakage, and this can happen when your analysis includes several steps. And so when an analysis includes several steps, you should split your fold before doing anything in your analysis, and in each fold, the whole analysis should be replicated. So a very simple example that sometimes you can see is that, for instance, you have a pre-selection of variable, and then these variables are used into a predictive model. If you do this pre-selection beforehand on your full data set, and then you do the cross-validation on just the part that is training your predictive model, you will have a very poor estimation of your generalization error. You will have something that is way too optimistic, and so you won't select the best model in that case. So really the whole analysis should be replicated here. And finally, cross-validation is also a good way to measure the error in, let's say, interpolating, in the sense that you need this all your data to be a good representation of the observations that can come later. If future data sets on which you want to predict, for instance, come and then but with very, very different features than the ones that you use to train your model and also to do cross-validation, then your cross-validation error might also be over-optimistic in how your model will predict for that. And so if this is something that can be the case, you might want to collect a new data set just for validation. Yeah. So to summarize all that I've said so far, when you build the model, machine learning model, it needs to be evaluated because you want to tune this model, choose the tuning parameters, and you want also to select what is your best model. And you also want to know their properties before deployment. So you create this model and then you want to give it to some colleagues in a hospital, for instance, to predict some outcome on patients or so on. You want to have a good idea of the error your model can make. And this evaluation needs to be done on a validation set. This means a set that has not been used to train your model. Otherwise, this will surely lead to overfitting and to a poor view of what will be the error of your model once it's used in practice. And cross-validation is an effective way to estimate this test error of a model with, of course, some pitfall that I just went through. Okay, well, thank you for listening to me. And if you want to go further into all of this, I strongly suggest to read these books, which, in my humble opinion, are the best on the topic. So this one is more of an introduction, if you really for newcomers into machine learning and all this topic. And this one goes deeper into many topics. And so if you're feeling comfortable to this one, I also recommend to go deeper with this one. It's a very brilliant book. Thank you very much.
Thank you, Bear, for such an insightful and valuable session. We've got a couple of questions in the Q&A box. Can you share a real-world example where machine learning significantly improved public health outcomes? I think Chewy would like to answer this question.
No, sorry. I just want to make it live. Sorry. Please go ahead.
Yeah. Okay. Yes, Bear, you can please answer this question. Can you share a real-world example where machine learning significantly improved public health outcomes?
Yeah. Well, maybe the example I'm most familiar with is in predicting exposure to air pollutants. So machine learning has been used really to improve our understanding how the pollutions, how people are exposed to air pollutants in areas where we don't have that many monitors to monitor air pollutants. So these are things that we have done in the team I am part of. Another example that is not the research I'm doing, for instance, is in identifying subgroups of identifying patients that respond well to a treatment. So this is more and more used where you have a new treatment, but some patients respond well to this treatment and others not. And so with their characteristics and so on, you can determine if your treatment will be good. I can see that probably Stefan has other example in mind.
Yes, exactly. I just wanted
Dr. Hugh wants to say something. Yeah.
I mean, just to complement what Pierre said, I come from an infectious disease background, and another application of machine learning is in drug development and drug treatment, for instance. Right. So there's a big field which that uses machine learning to that respect, for instance.
Yeah, thank you very much. The next question we have is, what kind of programming skills or tools should students focus on if they want to pursue a career in health data science?
That's a good question. That's a very good question. Well, maybe I'm a bit biased. Personally, I'm a big R fan and R users. So it depends. R is a very good tool, but for the focus of data science, and also if you really want to have a focus on machine learning, I would say that Python might be even more important. So I will go with Python, which is much more efficient for these very big models. Yeah.
And again, to complement from the program's perspective, so in the MSc Health Data Science, so we do have a programming module, right? A module dedicated to teaching programming skills, and we do indeed focus on Python and R, right? And I think it's fair to say that these are the two languages that are the most widely used in the field. So I mean, R is clearly, blooming, at the speed of light. But Python is also like a very solid skill, as Pierre said, who's is really ubiquitous. So it's very important for us that our students, once they graduate, are very at ease and familiar and proficient with these two languages.
Thank you. Thank you very much, Dr. Yu and Dr. Master, for answering this question. The another question that we have is, are there any opportunities for students to work on live research projects or data sets during the program?
Yeah, so I guess that's a question for me. So the answer is yes. In fact, we favor real data sets throughout the entire course. We think it's very important for students to be exposed to this, not only to understand, data governance, data cleaning, and just to be able to work with real life example. But we think this is the best way to prepare you and our graduates for, the professional world. So this happens in many cases, throughout in many points throughout the course. So most modules in the examples use real data sets, but we also have a module dedicated to actually handling, analyzing, a data set provided by external partners. So we have partners from a various range of institutions or context, from the industry, like pharmaceutical companies or governmental agencies, public health agencies, for instance, but also biotech companies, consultancy. They provide data sets for our students to work with. There's also the final summer research project, right, which will make each student to work on a unique, specific research question with a real data set. Again, by real, I mean not fake, but from the real life and taken from a real research context.
Thank you very much, Dr. Yu, for such an extensive explanation. I think we have another question. I think it's for Chewy, would be able to answer this. What scholarships are specifically available for international students in data science or machine learning related programs?
Hello everyone. So I think for this year, very unfortunately, I don't think we have any available scholarship because usually we run our scholarship from November to March, as it's almost to May. So I assume we don't have many available scholarship now, but I can just share our FHM scholarship page. So any of you, if wanted to explore more about our available funding and scholarship opportunities, please feel free to have a look there. Stephen, do you have anything to also advise in terms of scholarship and funding?
Yes, I do. So, we do have a range of scholarships available that our candidates can apply to. I can't give you from the top of my head the number of scholarships, and some of them are available across different programs, not just the health data science program. But there's quite a few. As Shui said, we have a page on the LSHTM website dedicated to scholarships. You can also find the full list with all the criteria, the prerequisites on the program's website. So usually, as Shui said, so the application period is between November and March. So sadly, for the next academic year, starting in September this year, 2026, the process is over. Right. But so we won't be able to kind of, offer, scholarships for this academic year. But there is a range. So there is, I don't know if you know how to access the website. I've got a QR code I can share or show on the screen if you want. But on the program website, together with all the relevant information about the program itself. There is a specific section on funding, fees, and scholarships where you will find all the information that is that you're requesting.
Yeah, thank you. I just shared the link of the page. So anyone who's interested in scholarship. Oh yeah, thank you. Thanks so much for sharing also sharing the slide. So please feel free to visit the page. So as Stephen said, we have all the conditions, criteria, and requirement. So please make sure you read through all the details. And I think, of course, if you have any question, you can also talk to StudyIn, and I believe that they can also help you with that scholarship issue. So I would just, if you visit the page, you can also see on the right-hand side, there is and sign up to our Vector newsletter. So also feel free to sign up our newsletter, and we will also share the latest information about the school, the program, and also the scholarship. So you will receive the newest update about the funding and the scholarship opportunities. Yeah.
And just to add, you can also send any questions or requests to me, directly. I'm more than happy to answer individual questions. In fact, a question addressed to the program through the website end up in my mailbox, so I'll be answering. But really, do not hesitate if you have any questions that we cannot address today.
Yeah, Stephen, I can just share the HDS email if you'd like to. I can share and I will also leave our study email address. So if you have any questions, please feel free to reach out to us.
Yes, please, Shui. I think that would be great. I think that brings us to the end of our masterclass. Thank you once again, Dr. Hugh and Dr. Maslow and Chewy for answering the questions. And thank you all to all our participants for joining us today. For more information about the London School of Hygiene and Tropical Medicine, please feel free to contact your StudyIn representative. Thank you once again, everyone, and have a wonderful rest of the day ahead. Thank you.
And
thank you, everyone. Thank you. Bye-bye.
Bye-bye.
Thank you.